Okay. Friday before spring break. Wow, you guys are hardcore. How many people are going away? Oh, good. Well, thanks for being here. I just thought, since it's the Friday before spring break, we just watch a little movie together. This is, how many people have seen The Social Network? Oh, good. Okay. So you guys may remember this scene. This is a little bit of your life today.
Suppose we're given a computer with a 16-bit virtual address and a page size of 256 bytes. The system uses one-level page tables that start at address hex 400. Maybe you went DMA on your 16-bit system. Who knows? The first two pages are reserved for hardware flags, etc. Assume page table entries have 8 status bits. 8 status bits would then be... Anybody? Let's see, we have our first render. Don't worry, Mr. Zuckerberg. Brighter men than you have tried and failed this class.
One valid bit, one modified bit, one reference bit, one permission bits.
That is correct.
So I actually, when I was at Harvard, this is supposed to be my, well, not him. You know who he is. This guy is supposed to be my advisor who was teaching the class at the time. And I remember seeing this film and looking at this slide in the back, right, and just thinking like, oh my gosh, I mean, because they hire consultants for these movies. I don't know if Matt actually gave them this slide or not, but I remember looking at it and thinking like, there's no way that that's a real slide from this class, right? Like it's just way too complicated, right? and then I was looking through Matt's old lecture notes when I was preparing mine for this course, and I found something that looked very much like that slide, right? So that was a real slide. So anyway, this is we're going to cover some of this material in class today.
That is correct. Does everybody see how we got there?
Does everyone see how we got there? How many people know what a page table entry is now? All right. How many people watched the video you're supposed to watch? So, if you guys remember, I'm really glad I didn't hold the midterm on Wednesday. That was a good decision. Thank you. And so the little video clip on Wednesday. So on Monday we had sort of convinced ourselves that this idea of dividing up memory into little equally sized pieces and using those pieces sort of as an additional way to manage memory sort of behind segments was a good idea, right? And now we're going to sort of start to deal with these sort of page monsters that we've created, right? And particularly, we've talked a little bit about the hardware, how the hardware works, and how the operating system uses these TLBs to efficiently and quickly translate page virtual addresses to physical frame numbers. Today we're going to talk about the process that the operating system has to perform in order to save all of this state about each process so that it can actually tell the hardware what to do, right? And if we get this far, we'll talk a little bit about what happens when we run out of memory and what a page fault is, and something called a hardware managed TLB, which you may or may not care about. You don't really have to care about for this class so much, but it's an interesting thing to talk about because a lot of TLBs are actually hardware managed, all right? And let's see if I can get this to work. It's going to be mad at me. Here we go. All right, so on Monday when you get back, next week is spring break, there will be no class-related activities, no office hours, no recitations, etc. Hopefully that's obvious. On Monday when we get back, we will do midterm review. The midterm will cover everything up through today. And on Wednesday, we will have the exam. The format of the exam will be pretty much the same as the exams that you can find online. There are several pre-existing midterms linked off the website, including a couple that have solutions. So those are good places to start. I think we've covered a little bit more material this year than we have in the past, so there'll probably be a little bit more about virtual memory than there have been in past exams, but the format will be the same. So it'll be 50-point exam, I think a bunch, 10, someone's got to tell me now, 10 multiple choice, a section of sort of short answer questions, and then a couple of medium, maybe 1 or 2 medium answer questions, and usually you get to pick one to answer. All right, any questions about the midterm exam? All right. Yeah, I just said that. Okay. So any questions about paging and page structures? The last 15 minutes of the lecture that I asked you guys to watch in lieu of Wednesday's class talked about page table entries, which we didn't quite get to on Monday, and this whole idea of paging and how to convert how to use pages as part of the process of converting virtual addresses to physical addresses, the benefits, blah, blah, blah. Questions about this stuff? All right. So remember, one of the things we liked about paging was this idea that we could maintain some of the structural organization of segments and just layer them on top of pages, right? So our segments can organize information about the process, allow us to figure out how to protect a particular range of memory addresses, whereas the addresses are actually translated on a per-page basis according to the mechanisms we talked about before, right? And one of the big challenges we had with segments, right? One of the problems with segments was that fixed size segments were difficult to move in and out of memory, right? Even if a process was only using a small part of a particular segment, I had to have that entire segment resident in memory, whereas with pages, now I can move pages around independently and have part of a segment in memory and part of a segment not, right? And I can have that segment mapped to all sorts of different parts of memory, right? And so I have less internal fragmentation. Do pages produce any external fragmentation? Why not?
Because all pages are the same size.
Because they're all the same size, right? So if I have pages that are all the same size, then I can never be in a situation where I can't allocate a page if I have a page available, right? I just put a page where I have one available. What were some of the issues with paging? Compared to segments, what were some of the drawbacks? Mac, what was one?
About the last slide.
Yeah, sure.
So you mentioned that it's not possible to have external segmentation or fragmentation, but what if you had like a page size of like 4 kilobytes, but you had 3 kilobytes of space in between each page? So then you could, within memory.
Don't do that. Yeah, no. So you would never do that, right? So what operating systems do is they break pages up. They break memory up into page-sized chunks, right? So essentially, I just divide memory into 4K pieces, right? So if I have 2 pages, the amount of memory between them will always be a multiple of 4K.
Okay, so you never do something.
So yeah, no. You wouldn't do that, because then you would have that problem, right?
Okay.
Don't create that problem for yourself. Yeah. There is one case, and some of you guys may find this biting you when you go to do assignment 3. There is one case where there can be some fragmentation issues with paging, but it has to do with the kernel's view of memory, and not with process view of memory, right? Processes always look at memory in terms of individual pages. Pages that appear to be contiguous to the process can be located anywhere in memory, and so I never have this external fragmentation problem. All right, good question though. Any of your questions about this? Yeah? Right, okay, there's one little sliver at the very end of memory, right, that I can't quite make use of, right? And so my suggestion is RAM makers make your memory in sizes of 4K, and they normally do, because it's like a megabyte. Right? So if you could buy like 1.03 megabytes of memory, right, then you'd have a little bit of extra memory there at the end. Right? And so yeah, it's like disks. You know, you always bought like a 1 terabyte disk and then you format it. It's like 750 gigabytes. And you're like, where did that stuff go? Right? It's a rounding problem, right? Okay, problems with paging. Yeah, Adam.
Is there a lot of overhead to allocate a page?
Why would there be overhead to allocate a page as opposed to a segment? No, I mean, there's certainly overhead to allocating memory, right? I have to potentially clear it out and stuff like that, but paging doesn't really produce any additional overhead, right? Yeah. Particularly with respect to segmentation, right? What about segmentation did we like that we sort of lost with paging?
It was easy to, you only had one comparison and one calculation to find the physical address of a virtual address.
Well, remember, now I'm going to use these really clever hardware. So the overhead to translating a page address, translating pages is actually a little bit simpler than translating segments, right? Because I can do this, fun trick where I just snap off 20 bits and replace them with 20 other bits, right? So on that level, it's a little bit easier, but you're going somewhere with this, yeah.
If the page isn't in the TLB, then you have to load in all the processes pages.
Well, so we're getting closer. What's one significant difference between pages and segments? Yeah.
The minimum you would allocate is 4.
Yes, that's true, but why is that a problem, Kevin?
If you have a program that needs a lot of memory, you have to allocate a lot of pages.
And with segments, I don't?
You might use more pages with segments.
Right, so remember with segments, a single, I could tell the hardware 3 pieces of information, right? the base virtual address, the base physical address, and the size. And now I can map, I've told the hardware how to map a potentially extremely large amount of memory, right? With paging, I have to tell, I have to tell the hardware 20 bits. I have to tell the hardware 20 bits for each 4K of memory, right? So the amount of memory that I can, so if you think about the amount of state that hardware has to hold, and that's limited, per unit of state, I'm mapping a lot less memory, potentially, right? Why was I OK with that? What property of programs made this work out OK? Why does it turn out that I can get away with not mapping large portions of the process's address space? With segments, I mean, you imagine with segments, hey, if I could tell the hardware about 8 segments, I might be able to map every virtual to physical address that process is going to use. That's pretty awesome. With pages, I'd map like 8 pages with the same amount of state, right? Why is that OK, Paul? Yeah, so I had this nice spatial locality property that I'm going to explain, which is that most of the addresses in use by a process at a given point in time, they can jump around over time, but they're pretty clustered in time, right? So a small amount of translations can translate a large amount of memory, right? This also required this per-page hardware translation, so I used the hardware to help us. And the hardware's ability to map memory is limited. Spatial locality helps me there. Today, what we're going to talk about really is this per-page operating system state, right? So you can think the TLB needs to know potentially a lot of different translations to translate a complete process address space. The operating system also needs to store all this information somewhere, right? With segments, I had just to, again, a couple of pieces of state I had to store in the operating system somewhere. Once I have per page state, I have some amount of information that I have to store per page. What did we call that? Or let's sort of do the end of Wednesday's lecture that you guys all watched online. So let's say the TLB creates a page fault, and the operating system needs to handle it, right? Or the TLB creates an exception saying, I don't know how to map this virtual address. So what do I need to tell the TLB in order to allow the TLB to map that virtual address? TLB says, hey, I've got this virtual address. I don't know what to do. What do I need to tell it? Let's assume that it's in memory somewhere. Yeah, James.
What physical page corresponds to the virtual page?
Yeah, where is it? Right? Where is it in memory? Right? If it's not in memory, I might need to do some other stuff, right? But if it is in memory, I need to tell the TLB, where is this address? Right? The TLB asks me, where does this virtual address map? Now with pages, what does the TLB actually ask me? The TLB doesn't necessarily map bytes to bytes. It maps what to what? Pages to pages, right? So it will say, where is this virtual page? And I'll say, here's this physical frame, which is what we sometimes call them, but they're the same size. It's 4K. So this requires that I store some information about each virtual page, right? So I need to know this information. What else do I need to do to make sure that this process is efficient, right? Because remember, when the TLB asks me for help, it means that something has already gone wrong. What went wrong? What would I have liked to happen? The TLB says, I don't know how to map that address, right? What would I have preferred the TLB do? Is that a trick question? Map the address, right? I wish it already knew this stuff, right? I wish I had told it a few minutes ago, or maybe if I told it, I wish it had remembered, or there hadn't been a context switch or something, right? So whenever the operating system ends up getting involved in address translation, you have to keep in mind you're already on a very slow path, right? The fast path is it's mapped directly by the TLB, and the memory instruction completes without the process even noticing, right? The slow path is that the operating system has to get involved. So the other requirement for page state is I need to be able to locate that state quickly, right? So I'm already slowing down the process. I don't want it to be like, oh, I don't know, where is the page? I don't know where I put that information about your page state, or I have like a linked list. Hey, I'm going to look through the linked list with every page in your address space. Just give me a few minutes while I walk it from, from head to tail or wherever the page is, right? And hey, maybe I'll walk it just to see if the page is there every time there's a fault. And if it isn't there, I'll be like, oh, okay, well, now I'm going to kill you. So remember, we called, and we'll refer to these frequently as PTEs, but we call these page table entries, right? And this tries to store all the information about a single virtual page, right? And what do I want? So every virtual page on the system will have a page table entry. So how many page table entries could there be?
Potentially very many.
Yeah, but yeah, that's really the right answer. Potentially a lot, right? There's no bound on this. It's essentially adding up the size of all the processes that are running, all of their allocated address space. Every virtual page used by any process on the system will have a page table entry. So what would I like these entries to be, ideally? Small, right? Very small. And this is one of the places, especially for assignment 3. I mean, we normally tell you in this class, like, it's okay to do things. Like, it's okay to have a linked list as your page table for assignment 3. If that's what works, that's fine, right? It's not going to produce a performance problem on your emulated OS 161 kernel, right? And if it helps you solve a correctness problem, I would say go for it. Page table entries are one case where it can be a little bit fun to do some clever engineering, because what we want to do is we want to cram as much information into these structures as we can, right? And normally we can do this into a 32-bit machine word, which is great, right? If I go to 33 bits, I've got a problem. Now I've got to allocate 64 bits, right? 31 bits, I've got a bit left over I could do something useful with, right? So ideally, I try to use 32. I need 20 bits for the location, right? Does everyone remember why this is? Why do I need 20 bits to determine the location of the page?
The other 12 bits are give the offset of the page.
Yeah, but what about pages? This would change if I changed what? The page size, right? This is a function of the page size. This is 32 bits minus the number that I need to map the offset, which is 12 because the betas are 4K, right? So I'm either, when I start using PTEs, there's either going to be two things I want to put in this location, right? We haven't talked yet about pages going out to disk, but I think you guys can imagine how that happens. But not every page used by every process is always located in memory. If the page is located in memory, I need the virtual page number, right? That's essentially, that's the information I'm going to tell the TLB when the TLB asks. If it's not in memory for some reason, and there's several different ways it could not be in memory. Sometimes there are pages that are sort of allocated to be filled in on demand with zeros, but let's just imagine the only other place the page goes is the disk, right? If it's located on the disk, I need some way of representing where it is on the disk in those 20 bits, right? I also can have some permission bits, right? So here I've got 4 bits I can use to mark it as read, write, execute. Maybe I only need 3 bits for this. I don't know why I put 4. Anyway. Valid bit, right? The valid bit helps me figure out, is this location a memory address or is it something else, right? I might use some bits to store state about whether the page has been used recently. This is something that we'll come back to after the exam when we talk about page replacement. And how many did that up to? I think I have some left over, right? 4, 1, 1. Yeah, sweet. I've got 6 bits left, right? So you guys can figure out what to do with those. I don't know. Use them to store the page's color, favorite color. I don't know. So yeah, so we usually jam these into a 32-bit data structure, right? And maybe I use, maybe the location of the page isn't as simple as something that can be represented in 1 bit. Maybe I need to use a couple of the bits for this, all right? So let's walk through the process that takes place when a process tries to address virtual address hex 10,000, right? So I've got these page table entries. That's great. I have a way of representing the state. I need to map them. So the MMU says, I don't know where this page is. I need help from the kernel. The kernel gets involved. And then, yeah, so this is what we don't want to happen, right? We don't want there to be this long delay where the kernel tries to figure out where is the information about this page, right? So there's really two requirements for this, right? And the data structures we're going to talk about today are essentially a compromise. They're not complicated, but they're a compromise between these two things, right? What are the, so I want, when I start thinking about designing a data structure to perform this translation or to be able to look up this information, what are the two things that I would ideally want that data structure to be, right? Okay, I want it to be fast. What else? Where is this data structure going to be stored? Memory. So it would be best if it was what? Small. Yeah, look at that. Wow. I said that all together. That was impressive. Yeah, so speed, right? I want to be able to do these translations fast. We already talked about that. But also compact, because this is kind of like scheduling. These data structures compete for useful memory with processes, right? So if I have a data structure that's really fast and yet massive, it doesn't work very well, okay? All right, so yeah, we got this. So the data structure that we use to do this mapping is called a page table, right? And we'll spend the rest of the day talking about a couple different designs for the data structure that we use to implement page tables, right? Every process has its own page table. That's another place where the compactness comes into play. Why is that true? Why does every process need its own page table? I should just be able to have one page table for the whole system. Yeah, I cannot translate. So this is where the process comes into play here. I can't translate a virtual address without knowing what the process is, right? So the thing I do to translate a virtual address is I get the page table for that process, and I use that page table to look up that virtual address. And that ensures that I get the page table entry that corresponds to this particular process, right? This is just a nice reminder about this. All right, so let's do the fastest approach, right? So here's the easiest thing to do. I use just one huge array. That array holds all the page table entries. I don't even really need to have pointers. I just have an array of page table entries, right? The virtual page number is the index into this array, right? So what's good about this? Simple. How fast is this? Right? So okay, I indulged myself and made a bunch of diagrams here. Okay, so there we go. So this is easy, right? And actually, like I said, I mean the page table entry would just be in here, but whatever. I wanted to get fun with this. Okay, so that looks like it works pretty well. What about speed? How long does it take to look up entries in here? Yeah. Yeah, it's 01, right? Because I use the virtual page number directly as an index. What about compactness? Kevin.
It's not very compact.
Yeah.
You can't make it grow as many processes.
Yeah, terrible, right? And remember, this is 4 megabytes per process. I shouldn't say remember. I mean, is that right? I'm pretty sure that actually that number is right. It's 4 megabytes to map a 4 gigabyte address space, right? The MIPS machine that you guys are designing on right now, like that might be the maximum. I think that's, well, I guess it's 8 megabytes, right? So if you put 8 or maybe 16, I think 16 is still the max that you can launch Sys161 with? I think it is. So at best, you could have 4 processes page tables, and they would consume all of memory, right? And the other thing is, on some systems, that again, this is sort of a little bit of something that will bite you on your system, that memory might actually have to be contiguous, because the kernel's view of memory is different than processes, and sometimes kernels don't have the ability to map memory in the same way, right? The other thing is, this is the same problem. The other thing that's bad about this, right? This is the same problem we had with base and bounds, right? Most of this array is unused, right? Most of the array consists of blank page table entries. But I still need all of it because the code is at one end and the stack is at the other, right? So here's the other extreme, right? So we'll start with the 2 extreme data structures, and then we'll talk about the one that's the compromise that systems actually implement, right? So a linked list, page table entries for each process, and I search it on each translation. Okay, so what's good about this? Well, actually, hold on. I think I have there we go. Sweet, look at that. How those page table entries came together. And then, I look through it on each, okay, there we go, and then Well, I guess I only did one. Yeah, so you guys understand how a linked list works, right? I don't know, I suddenly lapsed into thinking I was teaching 115 or something here for a minute. All right, so speed. How long does it take to look up a page table entry? Yeah, ON. You know, if I have n pages in my address space, so this probably isn't that bad, right? You know, what about compactness? That's pretty good, right? It's also ON, right? So it grows nicely. And every entry, this is the most compact data structure I could probably use for this, right? I might be able to do something a little fancier, but this is pretty good, right? Because I need some pointers, but in general, all entries in it are used. The search time here is the problem, right? And particularly as processes, address spaces get large and have lots and lots of page table entries in them, then I need to map all that memory. The speed here is the issue, right? And like I said before, for assignment 3, feel free to use linked lists for your page tables or something even simpler, because you know, this is not going to hurt your performance on the test that we use. Okay, but what real systems actually do is something that's pretty much a hybrid of these two approaches, right? And I build a tree. So multi-level page tables are, again, a fun source of exam question fodder. And what they do, and this starts to become very, I don't know what systems do with larger addresses, probably something similar, but a little bit different, because there's some features of this approach that are very, very nice fits for 4K, right? So what I do is I take the virtual page number and I break it into 2 parts. And each part is used as an index separately into a different part of the tree. So if I have 4K pages, my virtual page number is 20 bits. I use the top 10 bits as my index into a top-level page table, and the bottom 10 bits into the second-level page table. Don't worry, there's a diagram. And the nice thing about this is if I assume that pointers are 4 bytes, each page table is 2 to the 10 times 4 bytes, which is 4K. So each page table fits in, each sort of index of the page table fits in a page, right? So that's kind of cool. Okay, so that works, right? So here we go. So here's what I would do, right? I have now every process needs a first level table, right? But how many second level tables does every process need? Do you know? How many, like for this process, let's guess, how many second level page tables do you think it would need based on its address space? Maybe 3, maybe 5, maybe 6, right? I might be able to get all the code into 1, right? My heap probably sits in 1, and then maybe 1 each for these 3 stacks that are in use by my multi-threaded process, right? So the top 10 bits of this address that I'm trying to map identify an index in this first level table. And this first level table sort of, you could think of the index as pretty much laid out, associated with where things are in the address space. The second 10 bits are used as an index into my second level table, and that actually locates a PTE, right? Which are probably stored directly in the second level table if I can get them into 32 bits, right? Rather than using a pointer, it's more compact. Questions about this? Does this make sense? You guys could all solve an exam question on 2-level page tables. So what about our sort of complexity and speed analysis for this? How many lookups are required to translate a virtual page into, locate a PTE given a virtual page? Oh, it's still constant. Where's your log coming in? Yeah, this is important to talk about. This tree has constant depth, right? This tree has only 2 tables. There's no way to keep going up here, right? Like you stop right there, and there's only two lookups required for any, depending on the depth of the tree that you build. So for example, if I wanted to make the tree smaller, potentially, what could I do? What's an alternative design for multi-level page tables, given that I have a 20-bit virtual page number that I need to map? Yeah.
Divide the 20 bits up into smaller portions
Yeah, I could do like 5, 5, 5, 5, right? Now each element in my table is smaller, but the table's depth is growing, right? So yeah, but this layout is pretty much the canonical layout for most systems. I think with wider addresses, actually, I think x86 processors actually support 3-level page tables, right? And they have for a long time. The top level was usually not used, but as process address spaces have started to grow and as addresses have gotten wider, right, the top level is now actually part of the mapping process. So I have a constant number of lookups per translation. It depends on how I design my tree. And this depends on the sparsity of the address space, but it's somewhere, you know, it's much, much better than flat page tables and probably a little bit worse than a linked list, right? The real overhead here, right? If I have a process that has one address or one page that it's using, how many page tables do I need? How many indexes into the page table here? I have one valid page. Yeah. Two, right? So that's kind of the worst case, right? If as I start to add pages to my address space and they fall into those same tables, then I'm okay, right? So every process always needs a first level table and at least one second level table. And then depending on where the pages get allocated in my address space, this data structure hopefully grows pretty slowly, right? That's another reason for encouraging sort of the linking and loading tools to lay out address spaces as contiguously as possible, right? Because it reduces the size of the data structures that the kernel needs to translate. All right. OK, any questions about this? I know we covered this kind of quickly, but it's sort of like we've created a problem and we used a simple data structure to solve it. Yeah, that's a good day of work as a systems programmer, right? Any questions before we go on and talk about swapping quickly? All right, good. So far we've been really sort of talking about mainly translating addresses into core, right? But part of the beauty of the virtual address translation that we've been using to move things around in memory has been our ability to move things out of memory, right? Because it turns out that processes have typically a lot of memory or a lot of their address space that's not actively in use, right? So give me an example. I mean, why would this be, right? Give me an example of a process or an application that you might use on a daily basis and talk about some things that for you might be not stored in memory. How about, I'll just give an example. Yeah, go ahead.
What about installation software?
What's that?
Installation software.
No, OK, but I'm talking about a program that you're using. Yeah. OK, what would the virtual machine have that you're not using? Yeah, you see, you just made my question into a recursive question, right? Because now the virtual machine has stuff that's not in memory because the operating system underneath it has stuff in memory, but that's the question I'm asking, right? Yeah. What? There was an answer over here.
I was going to say, like, if you're using a web browser to cookies.
I mean, how many people think that they've used every feature that Firefox provides? OK. So where do you think those features that you're not using go? Should those features stay in memory? No. How many people think that they could even find if I gave you 4 hours every feature of Microsoft Word? Yeah, me neither, right? It's like there's always 10 ways to do something, and all of them are equally confusing. Yeah, I mean, they're like processes have a lot of code, right? And a lot of that code, even over time, as you're using the process, you guys have your own habits of how you use these things. And some of the code, some of the data structures that are associated with that. If you're using Firefox and you've got 68,000 tabs open, which I do all the time, hopefully eventually some of that tab content gets moved onto disk. And so the amount of, and there's a notion that that we use when we talk about virtual memory. And I don't think we cover this really in detail in this class, but this idea of a working set, right? So a working set represents the pages that a process is actually actively using, right? And a process's working set is usually a small fraction of its total the total amount of address space it has allocated. And even if you look at over time, right? I mean, to some degree, that's a function of spatial locality, right? But even if you look at it over time, there's still large portions of the code that never get executed, right? There may be portions of code in programs you use that you've never executed, right? There may be portions of code that actually can't be executed, right? Companies do this, what they call dead code elimination, right? There are software projects that get so complicated that there are code paths that can actually never be reached because it's like there's if, else, and like there's just a set of conditions that are required to get down this code path that will never be created. And companies run these tests to try to figure out if they're there so they can get rid of them, right? I mean, why have a lot of code sitting around in your application that no one ever uses and that's impossible to even reach, right? That's just sort of a waste of space, right? So anyway, at some point, we run out of memory, and we'd like to be able to move memory. We might be able to create more memory by removing some of the pages that are located in memory and putting them somewhere else, right? So where do these, what do we do at this point? I mean, there's more than one option. What's the simplest thing to do? What does your kernel do when it runs out of memory right now? Crash, panic, fail the allocation, whatever. Right? Thread fork starts to fail. Subpage allocator couldn't get a page, right? That's a fun error message to see. But what else could I do? Yeah. Yeah. So essentially, I can create more space by moving things to something else. Now, we've talked before about sort of classic system design techniques. So moving memory to the disk, for example, is almost starting to treat memory like what? Like a cache, right? The disk is bigger than memory, right? So wouldn't it be great, right? And let's talk about how we do this first. I'll get back to what's cool about it. So keep in mind, we may have to make sure when we're going to do this, we're going to move memory around, right? We have to make sure that it still obeys the memory interface, which means the last time the process used the virtual address, it behaved like memory. It loaded and stored values appropriately. And the next time the process used the address, it still behaves like memory. In particular, that memory has persisted its contents, right? If the machine shut down, whatever, right? All bets are off. But in the interim, the memory should have retained the contents that the preserved. Look at this. I had a better flow at this last year. OK. So we call the term we use for this is swapping, right? And essentially what this means is taking some of the disk space and using it to store the contents of memory in order to use that memory for some other purpose, right? So when I run out of memory, I can start to borrow memory from processes, move the contents of that memory to disk, and then I have available memory that I can use for some other purpose, right? To satisfy usually a new allocation, right? And to some degree now you can think about when I take the swap file plus the size of memory, I have this big chunk of space that I'm going to use like memory, right? The swap file actually also ends up getting chopped up into pages, right? Of course, I'm going to move pages of memory out to disk, right? And so I divide the swap file into little page-sized chunks. When swapping works well, right? But now essentially I have this storage space that's half memory, half disk, right? Some sort of like some Greek mythological creature, right? And it could be 10% memory, 90% disk. The ratios vary, right? This is usually something you can configure when you install your system. And the goal is to make your system feel like that it has as much memory as memory plus swap, but all of that space is as fast as the actual RAM on your system. If I don't do this well, what it ends up feeling like is your system only has the amount of memory it has, and it's all as slow as the disk, right? And this can happen, right? How many people have ever sort of gotten their system into this sort of state, right? When it's like sitting there and it's like the disk is going, and the bounce pointer is barely moving, right? We call that thrashing. I think I have Yeah, so and this is basically really highly dependent on choosing the right pages to write out to disk, and this is something that we will come back to not on Monday, but after the exam, right? So we'll talk about algorithms for essentially determining which pages should be moved, right? Before we're done today, there's a few other things that I need to clear up, right? Now that we're talking about swapping, we can make this distinction between what's called a TLB fault and a page fault, right? So when the operating system is asked to map a virtual address, there's two places that that data can be, or there's really only two places it can be that you guys should care about, right? One is it can be in memory somewhere, right? The second is it could be on the disk. In the first case, we call this a TLB fault, right? And what that indicates is that the only thing that the operating system needs to do to handle that fault is tell the TLB how to map that address, because the data is in memory, right? A page fault means that the virtual page either is not initialized, and we'll come back to that because there is this idea of doing on-demand page initialization, but the more common case is it's just not in memory, right? The operating system moved that page out to disk in order to create more space. I cannot have a page fault without a TLB fault. Why is that? What would be a very bad idea? Let's say I want to move a page out to disk. I pick my page. I move it out to disk. What do I need to make sure I do if I'm going to do this safely? Doug?
Tell the TLB that it's no longer a valid direct translation.
Yeah, I better get that translation out of the TLB. Because if I don't, the process is going to keep using it. It's just going to have some other contents in it, right? You guys laugh, but I guarantee about half the people who are laughing will do this for assignment 3, right? It's like, whoops, you know? Oh, suddenly you gave me some new data. That's interesting. I had not written that content in there. I don't know whose that is. Yeah. So, you know, and this, I shouldn't say cannot, should not exist for that. If the contents of page aren't in memory, then clearly there can't be a translation, right? But not every TLB fault will generate a page fault, right? Because if the page is already in memory, I don't need to go get it. I can just update the TLB and I'm done, right? There's also this, so this is not something you guys will encounter because your MIP system is what's called a software managed TLB. But there are actually architectures where the MMU is smart enough where it'll actually search the page tables that are set up by the operating system automatically to look for a valid translation. So what will happen is, instead of, so remember when the TLB needed help before, it was because it couldn't find a translation, right? A software managed TLB just gives up at that point. It says, I don't know what to do. A hardware managed TLB says, oh, I'm very clever, right? I know where the process page tables are. You have to tell it where they are. I know the format. You have to agree on the format with it. And I'm going to actually walk those page tables and see if I can find a valid entry for this virtual page number. If I can, I'll load it myself, right? And I will never tell the operating system that it happened. If I can't, or it usually means that either the address isn't valid or the page is on disk or hasn't been initialized. And in that case, I will ask the kernel for help, right? The pros of this is that hardware does this faster. Right? Clearly, I don't have to interrupt the operating system. The cons are that the operating system and hardware now starts to constrain the format of your page tables. So hardware has to know exactly how your page tables are set up and exactly how to walk through them and find the information it needs, right? So this provides the operating system with no flexibility about how to actually, so for example, if you were on x86, you're like, I'm going to write a linked list page table because that's cool. Nope, can't do it, right? The hardware does not know how to walk that page table. And what's important to realize is that on a hardware-managed TLB, the kernel actually never sees TLB faults, right? The hardware will only interrupt the kernel when a page fault happens, right? And yes, of course, and sys161, you have a software-managed TLB, and so you get to do all the fun stuff. All right, I'm done. I hope you guys have a great week off. Enjoy your break. On Monday, we will do midterm review. On Wednesday, we will have the midterm. And then on Friday, we will return to talking about sort of the last level of virtual memory, which is the policies that we use to create good performance by choosing which pages to swap to disk and which ones to not swap to disk.